So I was just telling about, in today's class, we are going to study about NaCl structure, CCM chloride structure to begin with. And then we'll move on to defects and properties of solids, magnetic and electric. To understand sodium chloride structure and cesium chloride structure, which is basically FCC and BCC respectively, we need to know about voids. We have studied, of course. That's what I was just giving a glimpse of it. So simple cube has particles at the corners. Amidst of 8 particles, there is a cubic void. If a particle, another particle occupies in that cubic void, it becomes a BCC unit cell. And that lattice can be called as body centered cubic lattice in 3 dimensions. Correct? Whereas in FCC, the voids present are not cubic voids. The voids present are tetrahedral voids and octahedral voids. Now, before studying sodium chloride and cesium chloride, let us understand which are all the positions of octahedral and tetrahedral void in a FCC unit cell. This probably you wouldn't have learned in your board discussion in regular classes. So that's why I thought of giving little more elaboration on this position of voids in FCC. Okay, so fine. Now, position of voids in FCC unit cell. Look at this. This is what kind of unit cell? Is it a FCC, BCC, or simple cube? Can anybody unmute and tell me? Which unit cell is this? Which unit cell is this? No idea?
Sir, is it FCC?
FCC, sir.
Okay, 1 second. What is this? One minute, I'm just checking at the technicalities here.
सर बताइए सर बताइए आवाज बताइए
ಬರ್ತಾ ಇದೆಯಾ?
हाँ बताइए सर बताइए
Okay, 1 second. Right. Okay. So let's proceed. So can you people tell me this unit cell is which one?
FCC.
FCC. Is it
FCC.
Okay, Ananya FCC, Bhumika FCC. Okay, Abhilasha FCC, and anybody else? This is not FCC or BCC, right? So this is
simple cubic cube.
It's not even simple cube, Mr. Neela. Okay, it is not even simple cube. It's a cube. That's all. Correct? No, it's a cube for the reason that there is no particle yet. So I just thought of asking you this. Anyhow, it's a just cubic unit cell. That's all. Now, depending on where exactly particles are present, then things will happen. Okay. So let's proceed. In order to call this cubic unit cell as FCC, particles must be there at the corners and all face centers. Correct. Now, we'll take a see where exactly the voids are present. Is the question. Octahedral voids are located at all edge centers and body center. Okay. Where is exactly octahedral void? They are located at all edge centers and body center. Can anybody tell me how many edge centers are there for a cube? How many edge centers?
12.
12 edge centers. So there is one body center. So 12 edge center octahedral voids and one body center. So let's see now. Look at that. So this animation can give you the brief idea. So these are the position of octahedral voids at the edge center, the top face, bottom face, and in between. So these are lighter ones just to make a difference. I have given light tinge, and the middle one, body center, octahedral. So these are all edge centers and one body center. So 12 plus 1. Now let us understand tetrahedral voids. So for that, let us clear up this octahedral voids. Now, where is tetrahedral void? Tetrahedral voids are located along the body diagonal. at 1/4 the distance against each corner. So when you take a body diagonal, what is body diagonal? Body diagonal is a line connecting two diagonally opposite corners. Okay, so you can look at the screen, follow the cursor. This is the corner I'm pointing out. Diagonally opposite corner, bottom is this one. Is that okay? So whereas the diagonally opposite corner, this one will be face diagonal. If it has to be diagonally opposite body diagonal, it has to be like that. Now if I keep showing the cursor like that, you may not be understanding. So that's why I have used different color lines here, so that you can easily understand body diagonal. So can anybody tell me how many body diagonals could be possible? Don't guess it, I'll remove that. How many body diagonals are possible?
4.
4. Good, good. Okay. So this is green body diagonal connecting diagonally opposite corners. Red one, yellow. There is a very much proximity in 2 dimension here, but as per the diagram it looks like that, but in 3 dimension there is clear distance between, equal distance of course, between red and yellow body diagonals also, and this is blue one. So totally 4 body diagonals are there. So I'll just read out again. Tetrahedral voids are located along body diagonal at 1/4 the distance against each corner. Look at this. Is it 1/4? Approximately. So you can see here, this is the corner, body diagonal against each corner at around 1/4 the distance. Tetrahedral voids are located. Is it okay? So now itself, can you tell me therefore how many tetrahedral voids could be possible? Anybody? How many tetrahedral voids could be possible therefore?
8, sir.
8. So 8. So because each body diagonal will have 2, so obviously 4 body diagonals into 2, there will be 8. You can see red one and yellow one, blue one also. Okay. So these are what tetrahedral void positions, right? Tetrahedral void positions. Now let's send them also, right? Now let us see all octahedral and tetrahedral voids together. So this is how it looks like. Okay, these are the positions of octahedral and tetrahedral voids. Sometimes we'll say in a particular ionic solid, one ion forms the lattice, another ion will be present in a void, either tetrahedral void or octahedral void. In the problem they would face a frame like this. So one negative ion would form the FCC lattice, and cation will be present in the 50% of tetrahedral void. So what is the formula? Correct? We have seen all this thing. Or all octahedral voids are occupied by cation. What is the formula? These kind of things. So I think you have understood the position of voids here. Let's proceed. So now important ionic solids. Here we are going to study with respect to CT importance, sodium chloride and cesium chloride structures. Okay. So come on. Structure of sodium. Okay. So FCC structure of chloride ions. That means sodium chloride has FCC structure of chloride ions. Na plus ions are not forming FCC structure. Chloride ions are forming FCC structure. Now, is it so? Why not Na plus? It is generally in any ionic solid, larger ion will form the lattice. The smaller ion, since it is small, it can be accommodated in a void. It always generally in ionic solids happens like that. Generally, larger ion will form the lattice, and the smaller ion will will be occupied in the void. In sodium chloride, which is larger, obviously chloride, for the reason that atomic number 17, in an atom 17 electron are there, but in the sodium chloride is Cl minus, one extra electron, 18 electron. So Cl minus due to extra electron, its effective nuclear charge is less and size is also more. Sodium atomic number 11, but it is Na plus here. As a result, sodium has 10 electron, 11 proton. Due to more effective nuclear charge also, the size is less. Okay. So Na plus is smaller, Cl minus is larger. Obviously, Cl minus forms FCC. When I say FCC structure is formed by chloride ions, what do you mean by that? Cl minus ions will be present at all the lattice points of FCC unit cell. Which are all the lattice points of FCC unit cell? Corner and face centers. Correct? No? FCC means particles or lattice points will be present at the corners and the face centers. So if chloride ion forms the FCC, chloride ions will be present at all the corners and face centers. And we'll see now. So chloride ions will be present at the corners and face centers. Where is exactly sodium ions? Sodium ions occupy all octahedral voids. What does it mean? So we have just told where and all octahedral voids are present in a FCC unit cell. If sodium ions occupy all octahedral voids, Na plus ions will be present at the all edge centers and body center. That is the meaning of that. All edge center and body center. Okay. Now let's see the structure. This is a cubic unit cell. All lattice points of FCC cubic unit cell is occupied by Cl minus N. All edge center and body center, that is octahedral void, Na plus. Okay. So now we'll see. Cl minus is large, hence represented by a yellow spherical particle like this. Okay. Na plus is small and is represented by a purple particle like this. Okay. So now we'll see how these particles are occupied there. Corners, face centers. That's all, no? Is there anywhere else Cl minus required, or that's all? That's all, no? All lattice points of Cl minus is occupied.
ಇಲ್ಲ ಇಲ್ಲಿ
Neelesh, tell me.
ಸರ್ ಹೆಂಗ್ ಹೇಳೋದು
ಹೆಂಗೋ ಹೇಳು ಪರವಾಗಿಲ್ಲ.
ಸರ್ ಅಲ್ಲಿ ಸರ್ ಇದ್ರ ಹತ್ರ ಹಿಂಗೆ ಹಿಂಗೆ
ನೀನು ಇದ್ರ ಹತ್ರ ತರ ಅನ್ಬೇಡ.
ಸೆಂಟರ್
ಓಕೆ, ಎಕ್ಸಾಕ್ಟ್ಲಿ ಲೈಕ್ ದಟ್, ನೋ? ಬ್ಯಾಕ್ ಫೇಸ್ ಸೆಂಟರ್ ಅಂತ ಹೇಳ್ತಿದ್ಯಾ, ರೈಟ್? Center. Okay. Then one back face center. That's all, no? Anywhere else?
ಸರ್ ಮುಂದೆ ಫೇಸ್ ಸೆಂಟರ್.
Front face center also requires one. So you can see one. So these are the lattice points. Anywhere else? That's all, no? So all corners and face centers are occupied by Cl minus. Now we'll take up Na plus. Edge centers. You can see side edge centers. All 4 edge centers have been occupied. And opposite face side edge centers have been occupied. And these are the edge center above and below. That's all, no? Is there anywhere else Na plus required? That's it. Right?
So body center.
Body center is required. This is Saad Sharif. Good. So now we'll take up one body center particle there. Okay. So now Na plus is there at the center of the unit cell also. So all the lattice points are occupied. So can you tell me immediately how many total number of particles, means lattice points, are there in FCC unit cell? You'll count, no? 1, 2, 3, 4, 5, 6, like that. You'll count. Just how many
14.
are in one vertical plane? 3, 3, 3, 9 into 3. There are 3 vertical planes, right? So 9, 9, 9, 9 into 3, 27 lattice points. If it is 27 lattice point, it is odd number. So one particle should be of 14, another should be 13. So can you tell me which is 14, which is 13? Okay, I'm getting some chat response. Bhumika. Oh, is it mic not muted? Okay. So those who require to speak, please only unmute. Otherwise, okay. Now, so 27 lattice points are there, 9 into 3. So can you tell me which is 14, which is 13?
Chlorine 14, sodium.
Chlorine 14, sodium 13. Exactly. So now chlorine 14, how it is? 10 plus 4, 12 plus 4, 13 plus 1. How is that exactly? 14. 14 can be any way. Yeah? 7 plus 7 is also 14. That is the way? It should be 8 at the corners, 6 at the face center. It should be 8 plus 6. That is 14 here. Okay. 13 Na plus. Where is exactly 13 Na plus? How is that 13? 12 plus 3.
12 plus 1.
12 plus 1. So 12 at the head centers, 1 at the body center. It is 12 plus 1. Okay. So very good. So I think you have understood this one. We'll proceed. We'll see some of the related calculations for NaCl structure. Okay. So some of the related calculations for NaCl structure. Now, just now I have told you number of lattice points 14 Cl minus 13 Na plus. So particles per unit cell. This concept is important. See, we say in FCC number of particles per unit cell is 4 because it is 8 into 1 by 8 plus 6 into 1 by 2, right? So it is 4. But here two types of particles are there, Cl minus and Na plus. So we need to calculate particle per unit cell of Cl minus as well Na plus. So now we'll proceed. Particle per unit cell of Cl minus. Cl minus is there at the corners. Share of a particle at the corner 1 by 8. Cl minus are also at the face centers. Share is 1 by 2. So it is 1 plus 3, 4. 4 Cl minus ions are there in 1 FCC NaCl unit cell. That's the meaning. But what's our 14 Cl minus are there now? All 14 Cl minus doesn't belong to the same unit cell completely. We know that because in NaCl solid, the unit cells are three-dimensionally surrounding one another. So that being the case, every particle at a lattice point would belong to one or more than one unit cell. That is what the calculation here. Okay. So from 14 Cl minus, it is like having only 4 Cl minus per 1 FCC NaCl unit cell. Right. Number of Na plus ions per unit cell. Okay. So now you know what is that? A particle at the edge center will have 1 by 4 share for the reason that it belongs to 4 unit cells there. So if you see the calculation, Na plus ions are there at the 12 edge center. The share is 1 by 4. And there is one particle at the body center. It completely belongs to the unit cell. Share is 1. So totally 3 plus 1 plus. That is 1 plus 3. This is 3 plus 1. 4. That means in one FCC NaCl unit cell, there are 4 Na plus 4 Cl minus. So 4 Na plus 4 Cl minus will be equal to 8 NaCl. Am I right? So in one FCC unit cell of NaCl, 4 Na plus 4 Cl minus is equal to 8 NaCl. Am I right or wrong?
4 NaCl, so it has 4 formula units.
Exactly. So because some people will, of course, in my regular class, I would interact like that. Here it's not possible. I'm missing that interaction. Anyhow, 4 Na plus is equal to 4 Cl minus 4 plus 4, 8, we would say. It is not so. One NaCl has 1 Na plus and 1 Cl minus required. So totally 4 Na plus 4 Cl minus will make only 4 NaCl formula units. So in one FCC NaCl unit, there are 4 NaCls overall from all 14 Cl minus and all 13 Na plus. That's the meaning of it. Fine. We'll proceed. Also, we should know this. We'll take one data that we know already. One molecular mass of any substance contains Avogadro number of particles, we say. For example, ammonia 17, correct? No, 14 plus 3, NH3. So 17 grams is one molecular mass is equal to Avogadro number of ammonia molecules, we say, like that. For NaCl, we more correctly, we should pronounce the 58.5 gram, which is the, generally we say for other molecules as molecular mass. In case of ionic solids, it should be called as formula mass because NaCl molecule doesn't repeat. Ions will repeat there. We'll find out the ratio. Since Na plus Cl minus is 4:4, it becomes 1:1, and thus the formula is NaCl. But that doesn't mean that NaCl molecules are there repeating to produce the solid. It is actually Na plus and Cl minus. That's why for ionic solids, we refer it as a formula mass rather than molecular mass. Of course, in our usual conversations, we sometimes say molecular mass, that's fine, understand. So 58.5 grams of formula mass of NaCl is like one molecular mass would be equal to or containing Avogadro number of NaCl molecules. Now, similarly, what is the mass of one FCC unit cell of NaCl which contains 4 NaCl units? So mass of one FCC unit cell of NaCl is equal to 58.5 into 4. Why 4? 4 NaCl units are there in one FCC. So mass of one FCC unit cell would be 58.5 into 4. Now that is like the formula mass of FCC unit cell. So that will be equal to Avogadro number of, what would you say? Avogadro number of FCC unit cells. See, there is a slight difference between saying 58.5 gram of NaCl contains Avogadro number of NaCl molecules, whereas 58.5 grams into into 4 grams would contain Avogadro number of FCC unit cells. So that difference you need to understand and remember. Okay. So they may ask you if 58.5 into 4 gram would contain Avogadro number of unit cells. How many unit cells are there in 1 gram? How many unit cells are there in 58.5 gram? These kind of questions are common. Okay, so that's why. Hope you have understood. Now let us comment on radius ratio in case of NaCl. Radius ratio of NaCl is 0.52. What is radius ratio? Radius of cation to anion. So radius of cation, Na plus divided by radius of anion, Cl minus, it amounts to 0.52, which lies in the radius ratio range 0.414 to 0.732. You have to remember the table last class I've given. In this range, if radius ratio is there in an ionic solid, the coordination number would be 6. That means every Na plus ion will have 6 nearest Cl minus ion. Every Cl minus ion will have 6 nearest Na plus. You can either say coordination number Na plus is to Cl minus is equal to 6 is to 6. Since it is same number, you can simply say 6. We'll proceed. Now, it is the structure of cesium chloride. Structure of cesium chloride.
Sir, I have a doubt, sir.
Yeah, tell me.
So, what is the effect of change in temperature and pressure on NaCl structure, sir?
Exactly. See,
Some nature will
coordination number and the structure would change in case of some ionic solids, for the reason that when you change the temperature, increase temperature at moderate pressure or decrease in pressure, so what would happen? Number of ions will move out. Okay, the probability of having less coordination number will be there. So here coordination number in FCC would be 6. It will change to BCC. Similarly, at different condition, BCC changes to FCC. So such kind of transformations would be seen with temperature and pressure in ionic solids. Is it okay? So that is always possible.
Okay, sir.
Right. Now it has BCC structure. So which is that cesium chloride is having BCC structure. Now there are 2 ions. BCC structure means which will form what? See, it is simple structure rather. Unlike a sodium chloride, there is no much complicacy here. Cl minus ions will form simple cube. Means Cl minus ions will be there present at the corners. Now, when 8 particles are there at the corner, there is a cubic void at the body center. That will be occupied by other type of ion, that is cesium ion. Is that okay? So it has a BCC structure where chloride ions are all present at the corners and cesium ions occupy cubic voids, which is also called body centered cubic void. Now the thing is, cesium is a large ion actually. Is that okay? You can see after cesium it is francium in the first group. So it has very much considerable ionic radius compared to Cl minus. So when such a large ion has to be accommodated at the midst of 8 ions, the particles Cl minus at the corners have to move away from each other at the corner. Okay, the particles have to move away from each other. That's why when cesium ion is there at the body center, particles Cl minus at the corners, they will be away from each other. They will not be in contact with each other. Then which are the particles in contact with each other in BCC? Particles along body diagonal will be in contact with each other. That's how exactly we have got an expression 4R is equal to root 3A in packing fraction calculations, right? We'll see the structure now. The Cl minus here is relatively large. It is yellow spherical particle represented like that. Cesium ion is larger. It is a purple particle. Now, where exactly is Cl minus? At the corners, like this. Where is cesium ion? It is there at the body center, like this. So this is how the cesium chloride structure is formed. Okay, right. Now some calculations pertaining to this. Since only simple structure is there, calculations are also not as much as NaCl. Number of lattice points: 8 at the corner Cl minus, 1 at the body center cesium ion. So 8 plus 1, 9. Now particle per unit cell. For Cl minus, 8 at the corner, share 1 by 8. It is like having that. So 1 particle per unit cell. Though there are 8 Cl minus, it is like having 1 complete Cl minus in 1 FCC, BCC unit cell. For CCM, 1 particle is there at the center completely. So 1 into 1, 1. So that particle completely belongs. So in one BCC unit cell of CCM chloride, there is one Cl minus, one CCM ion. So how many formula units are there in one unit cell? One CCM chloride formula. So hence, in one BCC unit cell, there is one CCM chloride formula unit. In case of sodium chloride, it was 4. Now radius ratio means the radius of cation CCM to the radius of anion Cl minus. When you take it becomes 0.93. 0.93 is in the range of radius ratio 0.732 to 1. So where coordination number in such ionic solids will be 8. So that means each particle will have 8 nearest particles. So every Cl minus will have 8 nearest CCM ion. Every CCM will have 8 nearest Cl minus ions in 3 dimension. Here it may not be seen. If you want to see here, you just have to consider CCM 4 above, 4 below, like that. In 3 dimension, every chloride also will have 8. For example, if you can imagine, just look at the screen and the cursor. So this is 1, adjacent unit cell 2, above unit cell 3, above unit cell 4. In front 4. Is that okay? So 4 plus 4, 8 CCM ion will be near to each Cl minus also. Not to worry. These are all the data which you have to remember. Let's say you got confused. Still you remember the data correctly, you got the marks. I'm not promoting to not understand, but don't get tense, that's all. Okay? So just have the conclusions, summary of entire data. Fine. So we'll proceed further. So that's about BCC structure, NaCl structure also, right? That's about the 2 unit cells that would be given in CET examination based on that. So now we'll see remaining concepts in solid state, defects and electrical magnetic properties of solids. Now, what is actually a defect? We know that in a solid, particles are arranged in 3 dimensions in a close packing manner, right? And some of the arrangements are very efficient, some of them are inefficient. In case of inefficient arrangement, there will be more void spaces, wastage of space. In case of efficient, there will be less. Then in some cases, under normal conditions of temperature and pressure, particles which are very neatly, regularly arranged in their lattice sites, in some cases, particles wouldn't be present in their lattice sites. They would be either absent or they will be occupied somewhere in the void, somewhere at other point in the solid itself. So any deviation in the regular arrangement of particles in a solid is called a defect. Okay, any deviation from the regular arrangement of particles is called a defect. If there is extra particle, it's a defect. If there is absence of particle, there is a defect. If particle is there not in the lattice side but just adjacent, it's a defect. So everything, if there is an impurity atom, it's a defect. So any deviation from regular arrangement can be defect. That's okay. So fine. Now defects can happen at a lattice point. If defect happen around a lattice point, then it is called point defect. Along a line of particles, line defect. Along the surface defect, volume defect, like that different defects are. In our syllabus for board and CET, we need to know point defects. So point defects means the defects which are happening in and around the lattice point. Okay, fine. Under point defects, you have stoichiometric defects, non-stoichiometric defects, and impurity defects. Okay, so we'll see one by one and brief up under every case. Right. Stoichiometric defect. Stoichiometry means what? Stoichiometry is a branch which deals with mole proportion, composition, formula related to that, calculations, all those, correct? Stoichiometry generally gives mole proportions, composition. Stoichiometric defect means the defect which doesn't affect stoichiometry or formula or composition of the solid is what is stoichiometric defect. That means despite of the defect happening in the solid, formula doesn't change. For example, NaCl, after some defect, if formula remains as NaCl only, then it is stoichiometric defect. If formula changes after the defect, then it is non-stoichiometric defect. Okay. Stoichiometric defect means doesn't affect stoichiometry, composition, mole proportion, this. Under stoichiometric defect, there are two types, each in non-ionic and ionic solids. For example, non-ionic means covalence, which contain only atoms in their lattice sites. Ionic is NaCl, CCM, chloride, all this. So in non-ionic, there are two types of stoichiometric defect. In ionic, there are two types of stoichiometric defect. We'll see now in this diagram. So in non-ionic, that is covalent, there are two types of stoichiometric defects. One is vacancy defect and one more is interstitial defect. So what is vacancy? As the name itself suggests, vacancy means having some voids. That's all. See, during the formation of solid itself, sometimes it so happens that some particles would be missing, wouldn't have occupied the lattice sites. Okay. So if a particle is not occupying a lattice site, then it can be called a void or vacancy, something like that. So this is a vacancy defect. You can see here, there is a void. There is no particle there. Okay. So interstitial defect. In some cases, what would happen? Extra particles would come and occupy in the void spaces. In such cases, it is called interstitial defect. So now vacancy defect means particles would be simply absent. How many, all those things doesn't matter for the reason that it is a covalent solid, non-ionic solid. Let's say there are 1,000 particles in a lattice, 10 particle miss out. Like for example, graphite. If 10 carbon miss out, formula still remains carbon only. Okay. Like that, if 10 particles are extra present, formula still remains carbon, but density alters. So when number of particles miss out, in the given volume, mass will be reducing. So density decreases, here density increases. So that difference happens. Okay. Now in ionic solids, similar defect, vacancy and interstitial defect in ionic solids are called a Schottky defect and Frenkel defect. Now, as I told you, Schottky defect is similar to vacancy defect. That means particles are absent. But the problem is, this is an ionic solid. Simply any number of particle, any particular ion cannot be absent. If some 10 Cl minus are absent and 5 Na plus are absent, electrical neutrality becomes a matter of concern. Any solid will be stable when they are electrically neutral. So total positive charge due to cations should be equal to total negative charge due to anions. So that point you have to remember while giving the statement for impurities in ionic solids. So in case of ionic solids, similar vacancy defect kind of thing happens, but equal number of cations and anions will be missing the lattice site. That is very important. You can see the pic here. The picture clearly depicts, see which is the ion here, the larger, smaller. The larger is minus. Okay, smaller is plus. NaCl, for example. Cl minus is purple here, and little pinkish is Na plus here. So you can see this. This position is Cl minus, and one Cl minus is absent means to maintain electrical neutrality, there should be one Na plus somewhere should be absent. So one Na plus is also absent. So total loss in negative charge is 1. Total positive charge loss is 1. So electrically, it is still neutral itself. Okay. So pairs of ions will be missing from the lattice side, creating vacancy. That is what is Schottky defect. Then Frenkel defect, some cation will be missing from its lattice side and will go and occupy. You can follow the cursor. Will go and occupy the interstitial side or void space. Okay. So that means the particle will be there well within the lattice itself. It will not go out of the solid. It will be there in the solid.
What problem is there, sir?
Okay.
What problem is there, sir?
Is it so for everybody? One second.
Yes, sir.
Yes, sir.
Now, is it audible clearly?
Yes, sir. Now it is okay.
I think it should be fine. Now, in case of Frenkel defect, some cation will be missing and occupied in a neighboring void space. So since particles doesn't go anywhere, here pair of ion missing or occupying, such kind of concept doesn't arise here. Okay. Simply some cation will be missing from its lattice side and will go and occupy in the void space. So between the two, both will maintain electrical neutrality. But the problem is in Schottky defect, since particles are missing, then the density would be affected in case of Schottky defect. So density decreases as Schottky defect increases. In case of Frenkel defect, density doesn't affect. for the reason that overall mass remains the same. Particles are just shifted, dislocated. So as a result, density remains same, electrical neutrality remains. But one important thing is, as defects increases in any solid, stability decreases. So more the defect it is, lesser is the stability. Okay. So this is about stoichiometric defect in non-ionic and ionic crystals. Fine. We'll proceed. Now defects in non-stoichiometric defects. So what are non-stoichiometric defects? These defects affect the stoichiometry. They affect the stoichiometry. So when these defects exist, the mole proportion formula will change. That's the meaning of it. Okay. Now we'll see now. There are two types. See, non-stoichiometric defect can happen due to metal excess and metal deficiency. Now again, it is ionic solids. An ionic solid will have generally a cation, which is a metal, an anion, which is a non-metal. Here, metal excess defect means more number of positive charges. That's how exactly you would understand. Metal deficiency defect means less number of positive charges. So, non-stoichiometric defect can happen in two ways: having more metal ions and having less metal ions. Metal excess defect, metal deficiency defect. We'll take up metal excess defect. Again, metal excess defect can happen due to two reasons. What is that? Let's say in an ionic solid, there is 100 cations, 100 anions. How metal excess can happen? Two ways. One, instead of 100 cations, if there are 102 cations, then metal excess. Anions are 100 only. 100 cations becomes 102 cations means, obviously, metal excess will happen. Cations means metal. Another way is 100 is there is no defect. 98 anion, if two anions are missing, then cations is 100, anions are 98, so then also metal is excess. So there are two ways: having excess metal or having less anions, like that. It's a common sense, right? So due to anionic vacancies. What do you mean by anionic vacancy? Anion vacated. The lattice point of anion is vacant. So this particular thing is very important. Here, there is something called F-center concept. So due to anionic vacancies, some F-center will be formed. You know this. I'll just discuss while explaining this. I'll take this. So due to anionic vacancy is one. That means anions are vacating. Cations are as such. Anions are reducing the number. So metal excess happens. Due to interstitial cations, means extra cations are there in the solid. Where is the place for extra cations to be accommodated? In the interstitial or void space. So due to extra cations in the interstitial side, that is one thing. You can see this diagram. Okay, here A plus B minus, it is little faint. You can easily understand. Negative is purple, positive is yellow here. So A plus B minus, like that it goes. Now look at this. There is an electron in the site. Okay, so A plus B minus, like that. Yellow is B minus. So B minus is left its lattice site. So anionic vacancy. So when anion vacates its position, number of anions reduce, cations remain same, yet metal excess happens. But what is the question? In case of ionic solid, if one particular type of ion only is missing, then there is a problem with electrical neutrality. So how does the solid's electrical neutrality is maintained? The anion that vacates will have an electron trapped inside its lattice point. One electron will be trapped in the anionic vacancy. The electron which is trapped in the anionic vacancy is what is called F center. F represents Forbin center or Fob center. Forbin center means it is color center, like that. Because any solid which has an electron trapped in the anionic vacancy would induce color to the defective solid. So for example, NaCl will be sometimes pale yellow whenever it has this kind of F center electrons. Is that okay? So that electron which is trapped in the anionic vacancy will balance the negative charge of the missing anion. That's as simple. So total negative, total positive are balanced. It is electrically neutral, right? So that is F center. You can see here F center. It is marked there. You can easily understand. Not a problem. So another one, I just see this. See, due to interstitial cations, some cations will occupy in the void space. Then how do the electrical neutrality is maintained? Again, the charge, positive charge will be neutralized by the electron being occupied in the neighborhood of the void space. Okay, so one electron gets trapped in the neighborhood of void space where total positive negative will be balanced. Okay, for example, zinc oxide when heated, it decomposes to give zinc ions, oxygen escapes, 2 electron will be obtained, right? So 2 electron will be occupied like that. One electron will be trapped in the zinc site itself. One electron will be trapped in the void space. That also can happen. Both can happen. In such cases also color will be induced, right? So this is about metal excess defect due to anionic vacancy, less number of anions, due to extra cations means excess metal ions, right? Metal deficiency defect. Metal deficiency. Metal means again here it is cation. Metal deficiency also you may think that two ways are possible. Let's say in a non-defective solid 100 cations, 100 anions are. Metal deficiency means cation should be less, anion should be more. That can happen in two ways. One is 100 no defect, 98 cations, 100 anions. That means when cation number decreases, then metal deficiency can happen. If 100 is there, instead of that, 1 or 2 anions, 2 extra anions. Now the question is, where do that extra anion be accommodated? Obviously in the void space, but most of the cases, anions will be larger. The larger anions cannot be occupied in a smaller void space. That's why that second type, that is metal deficiency due to extra anion in the interstitial site, is not a general example. It is not often seen at all. So therefore, we have one prominent type here, metal deficiency due to cationic vacancy. Cations can just leave. Okay, you can see this beautiful diagram here. So this green spherical particle represents oxygen, and the pink one is Fe2 plus, and little orange is Fe3 plus. Okay, so now what actually happens? You can see this position. What should have been this position actually? If there were to be a particle here, what should have been this position? It should be a pink particle, that is Fe2 plus particle. But what has happened here? Fe2 plus is missing from its lattice side. Fe2 plus is missing from its lattice side. Now, if Fe2 plus is missing from its lattice side, what is the problem? 2 cations are lost. 2 positive charges are lost. Rather, one Fe2 plus is equal to 2 positive charges. It's lost. That has to be balanced now. In order to balance the loss of 2 positive charges, the neighboring Fe2 plus ions gets oxidized. So how much is the charge lost? 2 positive charges lost. So this is one Fe2 plus gets oxidized to Fe3 plus. The another Fe2 plus also gets oxidized to Fe3 plus. So 2 positive charges thus increase in the entire lattice, balancing the loss of 2 positive charges due to Fe2 plus. Thus electrical neutrality is maintained. So in the previous cases, metal excess effect, electron trap will balance the charge. In this particular case, oxidation of neighboring cations will balance the loss of charge. That's how generally you can remember. So this is the other type, as I told you, accommodation of a anion in the void space is not a possibility for the reason that anions are generally large, voids are very small. They can only accommodate cations. So that's why we are not discussing. Let's proceed then. Now you can see this one example. FeO is ferrous oxide. When it loses some of the Fe2 plus ions, then formula will change. The stoichiometry or mole proportion will change. So FeO, after having this metal deficiency defect, the formula would change to Fe.950 like that. Fe.950 indicates metal component is less. You can see the formula and directly tell what type defect is this. That is a metal deficiency defect. Is it okay? Suddenly unmuting video. So, okay. Don't unmute videos, please. Let's proceed. Fine. Now we'll take up next. Last one, impurity defect. Impurity defect, the name itself suggests you presence of certain impurities in the lattice. That's all. Impurity defect. So in some cases, when one solid is added with another impurity and heated, some host ions can be replaced by impurity ions. Okay. In such cases, impurity defect will be obtained. So presence of impurity in the lattice points of the host ions is what is induces the impurity defect. One example, well known in all the cases, this example will be given, that is strontium chloride when added to sodium chloride. So it induces strontium ion impurity into the lattice. Obviously, when strontium ions are present, some Na plus ions have to be replaced. So you can see this diagram here. There is one strontium ion. The strontium ion has occupied which lattice site? Obviously, after Cl minus, it should be Na plus. So Na plus lattice site has been occupied by strontium ion. So it obviously introduces impurity, so impurity defect. Now the problem is with electrical neutrality. One Na plus is equal to one positive charge. One Sr2 plus is two positive charge. When one Na plus is replaced by one Sr2 plus, total positive charge of the solid increased by 1 unit, one positive charge. To balance the electrical neutrality, neighboring Na plus also will vacate the place. That means for every introduction of one Sr2 plus, two Na plus will be vacating. One position will be occupied by Sr2 plus and one Na plus position will remain vacant. So for every Sr2 plus introduced, one cationic vacancy creates. If 100 Sr2 plus is introduced, 100 cationic vacancies. If 1 mole of Sr2 plus is introduced, obviously 1 mole of cationic vacancy, which is equal to Avogadro number of cationic vacancies, will be created. So based on this, you can see this cationic vacancy. I just have given tagging there. There is one question. This concept has problems, has been asked in competitive exams. See, question is just I'll read out. Pay attention. 0.5 mole of strontium chloride is added to sodium chloride. Okay. Calculate the number of cationic vacancies immediately. Anybody? I just now gave 0.5 mole of
Na
strontium
by
chloride.
2, sir.
Pranav?
Na by 2.
Na by 2. Very good. Avogadro number divided by 2. It is easy, no? How much? 6.022 means divided by 2. 3.011. Okay. Into 10 raised to 20. So that many. Now I'll just give the solution for this. Each strontium ion replaces 2 Na plus, of which it occupies one cationic vacancy. Correct? No? One Na plus vacancy is occupied by Sr2 plus itself and produce one another vacancy. So obviously, number of Sr2 plus ions present in the lattice would be equal to number of cationic vacancies. So 0.5 mole is 0.5 into Avogadro number, which is nothing but 3.011 into 10 raised to 23 cationic vacancy. These kind of things, right? Okay. Electrical property of solids. I'll just brief through. It's already 10:30. It's more or less became a fast mode of regular class itself. A CET class cannot be like this. I can do. I am also enjoying, not a problem. But time taken for completion of syllabus becomes more. Okay, so we don't know when it will be. After solid state, as per the schedule, you have to go through and prepare for the chapters well in advance, so that I just brief up and take up more questions. Let's not spend more on concepts. Okay, if any concept is doubtful, you can ask me, not a problem. But we'll take more questions. Right. Electrical properties of solids, conductors. Now, based on electrical properties, solids will be divided into conductors, insulators, and semiconductors. And conductors will have conductivity range between 10 raised to 4 to 10 raised to 7 Simon per meter, ohm inverse Simon, right? So copper, silver, aluminum, iron, any metal for that matter are conductors. And now semiconductors, whose conductivity lies between that of conductors and insulators, we say uh, the conductivity goes as low as 10 raised to minus 6 to 10 raised to 4 Simon per meter. Silicon, germanium are the two intrinsic semiconductors. So when it comes to insulators, so conductivity is negligible of the order of 10 raised to minus 20 till then. Okay, 20 zeros, 1. So which is quite negligible. So that is the conductivity. That's why we say they don't conduct. So rubber, glass, plastic, diamond, mica, and all those things. Okay. Now to account for the electrical properties of solids, band theory has been proposed. If you are an electronic student, you would know about band theory and how exactly it explains based on the energy gap between valence band conductor. But as a chemistry student, you should know how is that band form, which electronics people in PU level may not explain, or they may also explain. I don't know. So, but generally they say band and the energy gap, all those things. But being a chemistry man, let me just throw some light on how a band is formed. Okay, I'll just explain. I have not made a PowerPoint presentation. All these things. Now, molecular orbital. This band theory is based on MOT concept. Molecular orbital theory says that when two atoms have to combine, the atomic orbitals, SPDF, right? Atomic orbitals of combining atoms should undergo linear combination. Linear combination of atomic orbitals of combining atoms result in two types of molecular orbitals. One is bonding molecular orbital, another one is anti-bonding molecular orbital. Bonding has low energy, more stable. Anti-bonding has more energy, less stable. Now, for every two atom, two MOs will be formed. One bonding, one anti-bonding. For 10 atoms, 10, 5 bonding, 5 anti-bonding. For 100 atoms, 50 bonding, 50 anti-bonding. For n number of atoms, n may be trillions, billions, whatever. For n number of atoms in a solid, n by 2 bonding, n by 2 anti-bonding. This all n by 2 bonding molecular orbitals will have so much energy difference which is negligible that they all appear as a band of orbitals. All n by 2 orbitals higher energy. They all appear as another band of orbitals. Where do electrons are present? Generally in the lower energy band. So in all these metals, electrons prefer to occupy this lower band, that is valence band. So all lower energy molecular orbitals form the valence band. Electrons are found there. All higher energy orbitals are forming the another band, that is the conduction band. They generally electrons are not found. These two bands, valence band and conduction band, will differ by an energy gap, that is forbidden gap. The energy gap between the two will decide the electrical property. Okay, this diagram beautifully depicts the entire properties here. Okay, VB is valence band, CB conduction band. In case of metals, that is conductors, correct? There will be no energy gap at all because the conduction band would have overlapped with the valence band. So easily electrons can transfer from valence band to conduction. So the ease of electron transfer will decide the conductor, insulator, and all. What is a conductor? Which can conduct electric current easily because electron can transfer from valence band to conduction band as energy gap is not there because they are overlapped. Okay. In case of semiconductor, the gap between them is very small. So what is the characteristic of a semiconductor? You take a semiconductor, increase temperature, electrons start promoting from valence band to conduction band, and thus conduction also increases. Of course, in case of semiconductor, as temperature increases, conductivity increases. This is the reason. More and more electrons get transferred from valence band to conduction band, so conduction increases. Whereas in case of insulator, the energy gap between VB and CB is too much that upon increasing temperature, to any extent also, the electron cannot transfer such an energy gap, and therefore they remain not conducting. Okay, so conduction can be negligible. So this is in brief about band theory, right? Intrinsic and extrinsic semiconductor. These are all the things which you have studied in your lower levels also. So semiconductors, intrinsic means pure, extrinsic means impure semiconductors. Okay, intrinsic can be converted to extrinsic by adding impurities. Addition of impurities, doping. Impurities themselves are called dopants. So pure semiconductor are intrinsic semiconductor. Impure semiconductors are extrinsic semiconductors. Okay, so pure to impure, how do you do? Intrinsic to extrinsic, addition of impurity you have to do. Then it becomes extrinsic. What is the need for getting extrinsic, or what is the need to convert a pure element into extrinsic or impure? To enhance the conductivity. Sometimes the pure semiconductors conduct so feeble current that is good for nothing. So we need little more enhancement of conduction. So for that we add little impurity and increase the conducting capacity. That's all. So more electric current we want it to conduct. More means in the range of 10 raised to 4 to 6 minus 6, whatever, little more. That's all. So that it can be used in all electrical circuits. See, the semiconductors are there in every electronic circuit, maybe mobile, computer, or anything. Okay, so fine. N-type semiconductor and P-type semiconductor. There are two types of extrinsic semiconductors. What is N-type? Negative type is. So these are obtained by adding electron-rich impurities. Okay. So now silicon and germanium are 14 group elements. When you dope means add impurity. When you dope the 14 group silicon germanium with pentavalent impurities are 15 group elements, arsenic, phosphorus and all. So they will have 5 valence electrons. So that is what, in comparison with 14 silicon germanium, 15 group elements have excess electrons in the valence. That's why they are called electron rich impurities. So what actually happens? Then you get a N type. I'll give you in the diagram. P type means positive type. So here we are going to add electron deficient or electron deficit impurity. 14 group elements will have 4 valence electron. Add an impurity with 3 valence electron. That is 13th group element, like boron or aluminum. Now you can see this diagram beautifully. It shows this. So silicon has 4 valence electrons. So with neighboring 4 atoms, it will have 4 covalent bonds. 1, 2, 3, 4. If you can follow the cursor here. Phosphorus will have 5 valence electron, of which 4 will be used to bond with neighboring 4 silicon atoms, and 1 remains excess. And that excess electron will add to the overall conductance, thereby enhancing the conductivity of N type. N is negative because of this excess electron itself. Is that okay? So that is the thing. Now you can see here. In case of P type, we have added a trivalent boron into tetravalent silicon. Boron has only 3 electrons. These green dots indicate electrons of boron. It can make 3 bonds with the neighboring silicon in the lattice, whereas it cannot make 1 bond with the other silicon. In such cases, you can see there is a faint circle here that is called as a positive vacancy or a hole. Okay, so that is a positive vacancy. So this positive vacancy attracts the electrons from the neighboring sites. So the neighboring bonds cleave and diffuse into these positive sides. This adds to the overall conductance, thereby increasing the conductivity of P-type semiconductor. Is that okay? So that is positive vacancy, and this is excess electron here. So that's why we say excess electrons are major charge carriers in N-type, whereas positive holes or vacancies are major charge carriers in P-type. Is that okay? So this is magnetic properties. We'll throw some light on magnetic properties. Okay. So fine. Depending on the magnetic behavior of substances, they are classified as, paramagnetic, diamagnetic, and ferromagnetic is what we know. But we have 2 more classes also, right? So paramagnetic means weakly attracted by magnetic field. Okay. So some of the what is the reason for this paramagnetic behavior? Having unpaired electrons. Okay. So you take any ion or compound that is O2, not 0,2. Okay, is O2. Cr, it has electrons. So therefore, O2 is paramagnetic. Because of unpaired electrons, when they are kept in the external magnetic field, they are weakly attracted. Diamagnetic substance, when they are kept in the external magnetic field, they are repelled because they doesn't have unpaired electrons. So absence of unpaired electron is the reason for it. So you can see titanium plus 2 as 3d2, 2 unpaired electron. Titanium plus 4 has lost the 3d electrons remaining also. It has 3d0, 4s0. So no unpaired electron. So titanium tetrachloride is diamagnetic. Titanium dichloride can be paramagnetic. You know that. Okay. So cuprous oxide, not cupric. It is Cu plus here. Water, they doesn't have unpaired electron. They all behave as diamagnetic substances. Ferromagnetic substance. So strongly attracted by magnetic field. Okay. They even retain some magnetic field even after the removal of external magnetic. They retain some magnetic field or magnetic property even after the removal of external magnetic. Iron, cobalt, nickel, and all this. Right. So what is the reason? Reason for ferromagnetism is, see, there will be small areas called domains. Domains will have atoms with similar magnetic moments whose magnetic moments are all inclined in the same direction. Those domains are strongly magnetic in nature. Because of these kind of domain structure, this ferromagnetism is induced in some of the metals, not in all. Ferromagnetism is not a general property of metals. Rather, paramagnetism is a general property of metals. Ferromagnetism is seen in those
So what
metals
problem is
where
this,
the
sir?
domain structure is not. Okay. I can,
What problem, sir?
voice is discontinuous. I can hold on sometime and again speak.
Okay.
Otherwise, there is no
Okay.
I can do. I am already in the area where I can get better signals. Apart from that, I can see what can be done. This has become, so everybody is going for online, no? Okay, right. Hmm. Can you hear me?
Yes, yes, sir.
See, you people are not complaining. Prajwal only listens to me more. Prajwal only says it is not audible. That's good thing actually. Plus, Prajwal will get good ranking in seats. Huh? Okay. We'll proceed. What is this? Still, people are entering into the room. Prajwal?
Problem, sir. Today rain has come, no rain, network problems.
They have to commute. Huh? Okay, that's why.
Okay, sir.
Anyhow, we'll proceed.
Yes, yes.
Ferromagnetic substance. So strongly attracted because of this domain structure. Domain structure is the structural feature that is there observed in some of the metals, not in all. So iron, cobalt, nickel are best examples. Okay, right. Now anti-ferromagnetic materials and ferrimagnetic materials. These are the two substances which we need to study as an extra magnetic property. See, in case of anti-ferromagnetic, they have domain structure or magnetic moments similar to ferromagnetic.
Excuse me, sir.
Tell me.
Sir, still it is not audible, so it's breaking.
What to do? I say. Now we'll do one thing. How much ever class lags, that much time we'll extend at the end. Okay. Let's see this problem persists or not. Okay. Like say 10-15 minutes is wasted in between because of this. We'll extend after 11 o'clock, 11:15 till then we'll extend to compensate that. Okay. Fine.
So can I write on the board, sir, for them?
What?
Can I write on the board so that it will be easy for them? Write on the board.
What should I write?
Now, whatever
No,
you're speaking, you
problem
can write
is,
on that.
I don't know, digital pen is not there with me. That's why I'm depending on this PowerPoint. Okay, now we can't buy also.
No, not like that. They can use this on the screen. You'll be having
That is
the
there.
small pens.
Okay,
You can use that.
Prajwal, I'll speak to you later. Okay. So,
Yes.
this is antiferromagnetic substance. Antiferromagnetic, will have this same domain structure or magnetic moments as that of ferromagnetic substances. But the difference is these substances, the moment they are introduced into the external magnetic field, their magnetic moment become quite equal and opposite. They get cancel off. That means despite of having magnetic moment similar to ferromagnetism, ferromagnetic materials, the domain structures or magnetic moments, because of the cancellation in the presence of external magnetic field, they behave like diamagnetic. Okay, so that's why we would say simply they are repelled due to pairing up of electrons in the magnetic field. Okay, and that is the difference. Sir, then this diamagnetic is same? No, no, no. They will have magnetic moments in the absence similar to ferromagnetic, but they get cancel off each other in the external magnetic field. That's why this class is different. That is antiferromagnetic substances like MnO, Cr2O3 and all. Okay. Now ferrimagnetic. Here also similar thing happens. Their magnetic moments of electrons domains will be similar to ferromagnetic. But when kept in the external magnetic field, few of the magnetic moments cancel out, and few electrons magnetic moment will not be cancelled. Whichever electrons magnetic moment is not cancelled, they impart some feeble magnetic property to the material and make them behave like paramagnetic. That means weakly attracted. So what I have given this statement is weakly attracted due to pairing of few electrons in magnetic field. So that's the difference. Anti-ferromagnetic and ferrimagnetic, in the absence of magnetic field, they will be similar to ferromagnetic. In the presence, all magnetic moment cancels, then it becomes antiferro. Only few magnetic moments cancel, then it becomes ferrimagnetic. So examples we have to just remember. So these are the 5 magnetic properties of materials. You can see this diagram depicts alignment of magnetic moments or domains of magnetic moment of domains. So all in one direction. Because of that, net magnetic field will be more, and it will be in the applied magnetic field. It will be strongly attracted. Whereas in antiferro, you can see alternative spin or magnetic moments will get cancelled out. Whereas here, you can see all the electrons magnetic moment is not cancelled. As a result, net magnetic moment still will be remaining in ferrimagnet. It becomes weakly attracted. So we'll proceed next. Oh God, this is the time for MCQs. I have given you worksheet 1, worksheet 2 on solid state. In worksheet 1, I think we have worked out 21 questions in the last class. We'll take 22nd now, and we'll see how many can be solved, because 15 minutes extension you told, no, we are going to do that. So now 22. For an ionic crystal of the general formula AX and coordination number 6, the radius ratio value will be 1. If coordination number has to be 6 in ionic solids, what should be the radius ratio? Can I get a response in chat, please? Option B. Okay. Yeah, exact. Very good. So it is 0.732 to actually reverse, 0.414 to 0.732. Anyway, that's the correct answer. So option B. Next week. This is a problem you have to work out. A metallic element has a cubic lattice. Each edge of the unit cell is 2 angstrom. The density of the metal is given to be 2.5 gram per centimeter cube. The unit cells in 200 gram of the metal. How many unit cells are there in 200 grams? Come on, you can work out. There is edge length here, 2 angstrom. Convert that one into centimeter, because density is given in gram per centimeter cube. In 200 grams, how many unit cells are there? Find out mass of one unit cell from density. After knowing mass of one unit cell, you can easily calculate how many unit cells are there in 200. I want the answer. Okay. Any option? Any answer? Where is Siddharth Kamath? No response. Hmm? Ritu. Yeah. This is getting the class recording can be done. There are few classes which I have to do. See, because of this, see, I'm answering the question here. Somebody has started me. Can I get the class recording? Generally, we do that. But what actually happening in every class, either because of this weak signal, some videos will be discontinuous. And because of these technical glitches, video is not continuous. So I am finding a suitable video editing tool. I am in that work itself. I have got one or two like that, but they are not doing the better job. After editing, the quality would come down. HD becomes SD. So I'm just on that. It takes little time. Definitely, all these videos will be made available as soon as possible. Anil option A, Sanjana A, Durgashri. Okay. So most of you are giving A. Good. You have worked out. That's a nice thing. Hmm? And but I'm not getting from everybody. Huh? Okay. Let me check. Fine. We'll take the solution. Edge length is given to be 2 angstrom. That has to be converted to centimeter, as I told you. So 10 raised to minus 10. Take out 10 raised to minus 2. Minus 2 is nothing but centimeter. What remains is minus 8. So 2 angstrom is nothing but 10 raised to minus 8 centimeter. Volume of the unit cell is A cube. So edge length is A. A cube would give volume. So which amounts to 8 into 10 raised to minus 24. Mass of the unit cell is equal to volume into density. Correct? Density is mass by volume. So find out mass of the unit cell. Volume we know. Density they have given. So when you substitute and simplify, so you will get the value. Of course, you can keep it as it is. Finally, you can simplify this. 8 into 10 raised to 20 minus 24 is volume. 2.5 is the density. So you can keep it as it is. So that means this is mass of 1 unit cell. That means in this mass, there is 1 unit cell. So how many unit cells are there in 200 gram is simple arithmetic calculation. So mass of 1 unit cell is 8 into 10 raised to minus 24 into 10, 2.5. That gives mass of 1 unit cell in the numerator. Into 200 would give 1 into 10 raised to 25. So option A. So most of you have given correct option. Very good. We'll take it further. Next, come on. A solid A plus B minus has NaCl, NaCl close packed structure. The radius of the cation when the radius of the anion is 250 picometer. The radius of the cation when the radius of anion is 250 picometer. How do you go about it? A plus B minus has NaCl structure. Now radius of cation anion both will be there related to one another in a relation, which is that radius ratio. Come on, do it. Now radius ratio of NaCl I have given you that you have to remember. How much is that? Anybody?
0.7.
No, that is the range actually. You can take range approximately also you get it. Right. Solution will take. Anybody has got the answer? Now in the radius ratio table, if NaCl structure is NaCl, you know, if each particle will have 6 nearest particles, the void space is octahedral. So for that, radius ratio range is starting from 0.414 to 0.732. It should not be equal to 0.732. Up to 0.732 is what is octahedral bond. So if it is NaCl, you should use the coordination number 6 range of radius ratio. It starts from 0.414. So you can just, they have given radius of anion 250. Radius of cation is what they are asking. The radius of the cation. So it will be not 3.5, which will be option A. Okay. There is one more problem here. In a cubic lattice, each edge of the unit cell is 400 picometer, right? Atomic weight of the element is 60 and its density is 6.25 gram per cubic centimeter. Avogadro number they have given, even if not given, we know the crystal lattices. Now, how do we find from the density equation which type of crystal lattice is it? Rho is equal to, or D is equal to Zm divided by A cube n A. There is no term which directly gives which is the unit cell like that. So what do you calculate here? Anybody? What do you calculate here?
Value of Z.
Pardon me?
Z values, sir.
Z
Z
value.
Exactly. So come on, calculate Z value. If it is one simple cube, if it is two body centered cube, if it is four face centered, make it fast. Anybody has got the answer? Good, 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 good. Aditi ye, Siddharth ye, Neil ye, Saksha ye, Komal ye. Fine. Samhita ye, right? Okay. I think you have got the right answer. Okay, we'll take the solution. Just do A cube. It is given in picometer, but density again gram per cc. So see to it that you convert that one into centimeter cube. Pico is 10 raised to minus 12. So if you use 410 raised to minus 10, it becomes centimeter, right? So rho is equal to Zm A cube in A. So you can take Z is what we need to calculate. It's been kept as X here. So if you calculate X is equal to 4. X is 4 means Z indicates particle per unit cell. So number of particle per unit cell is 4 for FCC itself. So it is option A. Okay. We'll take up next. A solid has BCC structure. If the distance of closest approach between the two atoms is 1.73 angstrom, the edge length of the unit cell. Come on. This is BCC structure. They have given distance of closest approach D. You know D is equal to 2R. And R expression we know for every unit cell. So D has been given 1.73 angstrom. That must be angstrom. That 0 is missing there. The edge length of the unit cell is A there asking. This must take 30 seconds, not more than that. The sixth is option. I have given you here options. Now already option A. So quite fast. Good. Aditi. G. Disha from GI. Good. Good, good, good. Okay, but I think I have got good responses. We'll take up now. Uh, uh, Actually, the relation between R and A is 4R is equal to root 3A. But D is equal to 2R. If you substitute, you will get this expression. So D is equal to root 3A by 2. Right? So A is equal to 1.73 into 2 by root 3 because they have given D there. So it becomes 200 picometer because it is in angstrom. So 2 angstrom is nothing but 200 picometers. So option A is correct, as most of you have given. Now look at this. 27. For the structure given below, the site marked as S is tetrahedral, cubic, octahedral, none of this. (27C). Okay. You remember just now we have discussed. This is edge center. Edge center is the position of a octahedral wall. So it should be option C. That's fine.